Okay, so we will start today a new chapter, which is the chapter of work and energy. In this chapter, we will develop and apply the principle of work and energy, where this principle will relate force, velocity, and displacement. In addition, we will consider problems involving power and efficiency, and we will introduce the concept of a conservative force and apply the theorem of conservation of energy to solve some problems. So to start with, we will start by the definition of the work of a force. So in which case a force can produce a work when it has a component that is parallel to displacement. Okay, so if you look at the figure here, we are moving on a curved line. Then for a certain small displacement ds, okay, we should see to see if this force is doing a work or not. We should see if it has a projection on the displacement. So for example, here, knowing that the angle between a displacement and force is theta, if you project the force on the tangent direction, then you have that the projection will be f cosine theta. And then you can say that the elementary displacement, the elementary work of f is f cosine theta times the displacement df. This is why the definition of work can be done by the scalar product. So we can say that the elementary work of a force can be defined as the force scalar dot product the position vector, the displacement vector, sorry, dr. Okay, so here, in case the force is perpendicular to displacement vector dr, this means that no work. Okay, and in case it's collinear, then the work will be f times dr. In case f is directed along the displacement, so if they have the same sense, it's a positive work. If they have opposite sense, it's a negative work. Okay. Please stop me in case there is something not clear. Now, in order to determine the work done when we go from position 1 to position 2, so if you are moving from one position to another, when you move, you can define the position vector variation, and you can define also the curvilinear coordinate variation. So let us consider the following curve. Let's say you are interested in the work produced from position 1 to position 2. Since the elementary work du is defined as f dot r, so if you want to find the total work, you should integrate between position 1 and position 2. And then you can say that from work definition, which is du equal f dot dr, I can integrate over the position vector from r1 to r2 of f dot dr. And now, if I do the scalar, the dot product here, I can replace f dot dr by f cosine theta ds. And then I will integrate from curvilinear position s1 to curvilinear position s2 f cosine theta ds. Now, in case f is variable or theta is variable, then they should be provided as a function of s, so we can perform the integration. And in case they are constant, we can take them outside of the integration, and then we can say that for constant force with constant direction, the work will be f cosine theta delta s. Okay. Now, in case it's a variable, we need to have the function, and we do simple integration. Or also we can use graphical interpretation. So if you have the graph of, here you have the presentation of f cosine theta, function of s. You can define the work as the area under the curve, because by definition, integral of a function with respect to a certain variable represents the area formed between the function, the curved line, and the axis. Okay, so graphically, the work is the area under the force cosine theta, function of the displacement s. Any question until here? Okay. Now, let us take in particular the weight. The weight is one of the most important force that we face in problems. So we will determine together a general formula for the work of the weight. So now we will develop the work of the weight starting from definition that the work of a force is integral F dot displacement dr. And now by integrating between position 1 and position 2, we have first the weight, so it's minus wj. The weight is always vertical. If we consider y axis positive upward, then w will be minus wj. Now for the displacement vector dr, it can be decomposed into three components in ijk frame. So we can replace dr by dxi plus dyj plus dzk. And now we can say that the work, by doing the expansion here, you have j dot I 0 because they are perpendicular. J dot j, it's 1, and we have minus w dy. And finally, j dot k is 0. So you will only have, your integration will be only along y because the other terms are 0. So you have integral from y1 to y2 of minus w dy. Now, in case we are working uh, in a space where we don't have a large of variation in altitude, so if w can be considered constant because you know w is mg, and g depends on the height of the object. Okay, so or the altitude of the object. So higher is the altitude, g will decrease. Okay, but if we consider small variation in altitude, so we are not varying a lot, then g can be considered as constant because the altitude should vary in kilometers in order to have variation in g. Small variation will not affect g a lot because if you remember from definition of g, it is equal to the gravitational constant times mass of the earth over r plus h squared, where r represents the radius of the earth and h is the height of the object from the surface of the earth. So in case the variation of h is not large compared to, if you want, radius of earth, then we can consider that the weight will not vary a lot. Okay, now, so in general we consider the weight as constant إلا إذا هن عطونا إنه we have a satellite application and they gave us the variation of, or we can find the variation of g then. We can consider in cases where no change in altitude that w is constant. So taking w outside of the integration, we get that the work between 1 and 2 of the weight is equal to minus w delta y, where delta y represents the variation in position, y final minus y initial. Now, as you can see here in this formula, you should pay attention for the convention. So the work is given by minus w delta y in case your positive axis y is upward. Okay? While if you consider, for example, that y axis is downward, so in application where y axis is downward, then what will be the expression of the weight, of the work of the weight? بتصير plus. Yes, exactly. بتصير plus. لأنه كيف بتفرق الايكويشن معنا هون؟ بدل minus wj بتصير plus wj. Okay? Because in y, when y is considered positive downward, then the expression of the weight will be plus wj. And this will give us that the work of the weight is plus w delta y. So just keep in mind the convention you are taking, decide which formula to use. Okay? Now,
Okay.
yes? حدا كان عنده question?
لا.
Okay. So now, concerning the work of a spring force. Also, the spring force is very encountered in problems. So we need to develop the work done by a spring on an object. Now, Depending on the spring, we have springs that are elastic springs. And in general, linear elastic spring is characterized by F equals to K times delta F. Okay. In case it's not a linear elastic spring, they should give you how F is varying with the displacement. Okay. But in general, if they don't mention anything, it's a normal spring given by where the force developed is K times delta F. Now here we will try to define the work of a spring. Okay, please pay attention. When we talk about work, we should specify work of what on what. Okay, because here, for example, if you apply, let's say, a force on the spring. So let's say you put a ball, you do a certain stretching, then you leave your ball. Okay, the ball will do a work on the spring, and the spring will do a work on the ball, and by action reaction the two works will be opposite, just like the forces, because you know by action reaction the force of the spring on the ball is equal and opposite to the force of the ball on the spring. It's similar for work. Okay, so here in this example they are finding the work done on the spring, so always specify your system. If I want to determine the work done on the spring by the force F, then I should say, if I consider a certain stretching, okay, let's say I am performing a certain stretching, ds, okay, or delta s, and then I am leaving my ball. So what will happen? I will do a work on my spring. This work is equal to what? You know that when you if you are stretching your spring, then you are doing a first, let's say, towards the right. So this is a stretching force. Okay. If you apply a force Fs in this direction on the spring, you can replace. You can say that the stretching force can be given by, if you consider that S is counted from the unstretched position. Okay. So if S0 equal to 0 on the unstretched position, then S will represent what? S will represent the value of stretching. Okay. Or also compression, because you know that your spring will oscillate between the, stretching and compression state. So now if S is positive, my spring is stretched. If S is negative, my spring is compressed. Okay, and this is why I can make a general formula of F. F of the force on the spring. This is not a subscript. Okay, it is a K times S. So the force on the spring can be written as K times S. When Sn is positive, it's a stretching, so F is positive. And when S is negative, it's a compressive force, and the sign of F will automatically change to be towards the left. Okay, so this expression represents in both cases of tension and compression the expression of this force done on the spring. Okay, now if you want to determine what will be the work done on the spring, since this force is not constant, it's function of S, then you should perform integration. Okay, because it's a variable force. Then I go back to the definition. The work of a spring is given by elementary work is the force Ks times the displacement ds. Okay, and now I will integrate between state 1 and state 2. Therefore, the work of my force by integration, the integral of Ks is Ks squared over 2. Okay, so now when I integrate and I apply between the two boundaries, S1 and S2, I will get that the work done on the spring between 1 and 2 is half K S2 squared minus half K S1 squared. But please pay attention, I repeat, this is the work done on the spring. In general, we will not take as system the spring. What is more interesting for us is the ball. So if we want to determine the work of the spring on the ball, so by action reaction, it will be the opposite. Okay, so work of spring on ball will be just the opposite of the result we obtained here. So it will be equal to minus half k s2 square plus half k s1 square. Okay, so this is the only difference, because by action reaction we'll have opposite result. So work of the spring on the ball is just minus half k s2 square plus half k s1 square, where s2 represents the stretching or compression at the final state, and s1 represents the stretching or compression at the initial state. Okay, any question on this? Now, you can use also the graphical method to obtain the work, because look, here it's simple. You have that the function of the spring force relative to displacement, you have a linear function. Okay, so we have a linear variation. Now, between any two positions, S1, S2, I can say that, can you please mute your microphones? So if you consider any two positions, S1, S2, then you can say that the work done on the spring is equal to the area under the curve. Okay, and to calculate this area, you have the height, which is S2 minus S1 times the median base. So here you have KS1 plus KS2 over 2. So if you do the development, you will get the same expression of this work. Okay, graphically, this is a graphical method, this is the analytical method. So here it's a trapezoid, this is KS1, this is KS2. Let us do it together. So, and this is S2 minus S1. So if you calculate the area of the trapezoid, you will get that the area is equal to the work done on the spring, work between 1 and 2, is equal to the height, which is S2 minus S1, times this base here, which is the summation of the small base plus big base over 2. So times KS1. So I can take a K into factor. So it's K S1 plus S2 over 2. Now if you do the development, you know that S2 minus S1 times S1 plus S2 is S2 square minus S1 square. So you will go back exactly to the same result, okay? Where you have that the work done on the spring is half K S2 square minus half K S1 square. And I repeat, this is the work done on the spring. If you want to take the work done on the ball, you just take the opposite sign. Now, let us see some examples. So in general, any object can be subjected to several forces. So when you want to find the total work, you should find the work done by each force, and then you can add them in an algebraic way, because some of the works can be negative, while other can be positive. It depends on the projection of the force on the displacement line. So for example, here in this example, you have a cart and you are trying to moving it upward. So you are putting a force on it through the action of your hand. You will put a certain force on it. This force here is inclined. So, and the angle of the force with the line of motion is equal to phi. So if you want to determine the work done by force T, you should first project T on the line of motion. Okay, it is clear that the projection of T is in the positive direction of motion, and then you can say that the work of T will be then positive. If we assume that T and phi are constants, so we can take them outside of the integration, so we get plus T cosine phi times S, where S represents the displacement distance. So I'm moving upward a certain distance S. So the work of T is positive. Now concerning the work of the weight, so for the weight, you always have two methods. You can project on the line of motion and multiply by S, or you can use also the second method and both, of course, will give you the same result, that it is minus W delta Y. Let us try together to see that both will give us the same result. So if you apply first the projection method, here you have that your crate is moving on an inclined line, and the slope of the inclined line is theta. So for the weight, since the weight is vertical, it's perpendicular to the horizontal line, then it will do with the inclined here an angle of pi over 2 minus theta, and therefore the angle with the vertical will be theta. So this angle here is theta. So if I put it on a larger figure, this is the weight, this is the inclined line. The angle between the weight and the perpendicular here to line of motion is theta. Okay, so now if I want to project the weight on the line of motion, I will have a negative projection, and this negative projection is equal to minus W sine of theta. Since the projection of W is opposing motion, then the work of W will be negative. Okay, so to find the work of W, it is minus W sine theta, considering that small change in elevation, so W can be treated as a constant, times S. Now, in case you want to apply the other formula, minus W delta Y, we will still obtain the same result. Why? First, when you use minus W delta Y, your Y should be vertical upward. So this is your Y axis. Okay. Now, I want to try to relate delta Y to delta S. So you know that your your crate is moving upward. Okay. So let us consider that delta S will be in this direction. This is delta S. Okay. So this is delta S. And this is the corresponding delta Y in motion. And we know that the angle here is equal to, so you know that delta Y is doing with delta S an angle of pi over 2 minus theta. Okay. So this is pi over 2 minus theta. So now you can say that I can relate if you want. خلينا نرسمها مظبوط لأنه it's not to scale here. I will draw it in a better way. This is delta S along the incline. This will be delta Y. It will be the distance moved vertically. Okay. So this is delta Y and this is delta X, let's say. So, and we know that the angle between the horizontal and the incline is theta. So this is theta. This is delta S. This is delta Y. So from this figure, I can relate delta Y to delta S through this right triangle by saying that delta Y is equal to sine theta times delta S. Okay, sine theta times delta S. And then if I replace back into the formula of work of weight equal to minus W delta Y. So if I replace now delta Y by its expression, I will go back to the same result, that the work of the weight is minus W sine theta S. Here S is equal to delta S, since S0 is equal to 0. Okay. So by the two methods, we got that the work of the weight is minus W sine theta S. Now, what about the work of the normal reaction? What will be the work of N, the normal?
0.
Very good. Why? Because it's perpendicular to motion. So we know that any force that is perpendicular to motion will do a zero work. Okay, because by definition, the work is F dot, so it's integral F dot dr, and you know that for when force is perpendicular to displacement, then the dot product is 0, and this force cannot produce any work. Okay.
Doctor,
Yes. Yes, tell me.
دكتور باليوتين
Yes.
هي الورك اوف مين عميل؟
هي الwork of your hand على الكارد. يعني أنت your hand is acting on the card here. It's pushing it upward. Okay. So your hand is doing a force on the card. This is the work of your hand on the card. The weight is the work of the weight on the card. And for the normal, it's no work. And here you are representing the free body diagram of the card. So all works here are the work done by external forces on the card.
اوكي دكتور ماشي.
Well, let us do an application on work of forces. The 10 kilogram block rests on a smooth incline. If the spring is originally stretched 0.5 meters, determine the total work done by all forces acting on the block. When a horizontal force P of 400 Newton pushes the block up the plane a distance of 2 meters. So always when you have an initial state and a final state, and you have a displacement between, you know the displacement between the two, try to think about work and energy, and we will introduce after what is the principle of work and energy. Now, just in this question, they are asking to find the total work done by all forces when moving from a certain position to another. So let us put our states. We should define state 1, state 2. This is the original state. What do we know about the original state? We know that initially the spring is already stretched. Okay, so my spring is not unstretched at the beginning, it was already stretched 0.5. So we can write that delta S1 is equal to 0.5 meters. Okay, this will help us into assessing the work of the spring. We know also that we have a force P acting horizontally on the block. So now the first step will be to draw the free body diagram of forces acting on the block. So at any position, the block is exposed to P, to the weight, which is vertical, to the normal reaction, which is perpendicular to contact, and of course to the spring force. Okay, so since here my block was already stretched, I am stretching it more, so my force is a stretching force, and then the spring will do on a block a force opposing its motion, so it will try to push it downward. So this is F of spring. Now, since they said it's a smooth incline, this means that no friction. Okay, so we don't have a friction force. So now, in order to find the total work, we should compute what is the work of each force, and then we add them. And always remember, a force that has a projection along the displacement sense has a positive work, while the force having a projection أصلا فيكم تعرفوها من الدوت product. يعني you know that when two forces the projection of a force is opposing the displacement بيطلع الكوساين تتا negative, لأن cosine theta is positive between 0 and 90 and negative between 90 and 180. So if you have, for example, this is the displacement and this is the force, then the angle between them will be larger than 90, and then the projection will be negative. Okay, and it will do a negative work. While for angles between the force and the displacement between 0 and 90, work will be positive. Okay, now let us start with work of each force. Okay, the easiest one is the normal. The normal is perpendicular to motion, so work of the normal is 0. So we are done now with the normal. Now, concerning force P is a constant. It's constant in magnitude and in direction. So it has a magnitude of 400 Newton, and it's doing 30 degrees with the inclined line. Okay, so now since you are moving along the incline, then you should project your force P along the incline to find the work of P. So to find the work of P, I say that the projection of P on the incline is along the direction of motion, so it's a positive work. And since this angle is 30, so this angle, these are alternating angles, so this is 30 degrees, and then I can say that the work of P, so in general in English system, the work of P, the symbol of the work is U. So in Hebler notation, U represents the work of a force. So work of P is equal. Since the projection of P on the line of motion is in the positive sense, so it's a plus P cosine 30 times delta S. Okay, now delta S is given to be 2 meters. So all I have to do now is to replace delta S by 2, and I replace P by 400, so I can get the work of P. Okay. Now we still have the weight and the spring force. For the weight, as I told you before, you always have two choices. Or you project the weight on the line of motion. So as you can see here, for example, this is the weight. We know that the weight is doing with the perpendicular to the incline an angle of 30 degrees. So if I want to project weight on direction of motion, it will have a negative projection. And the projection is then minus W sine 30. So for the work of the weight, it's like the previous example. So it's just minus W sine 30 times delta S. Or if you want also another method is to say, I will use the formula minus W delta Y. If you want to use minus W delta Y, all you have to do is to find what is delta Y. Okay, so if we, let me erase so you can see it better. When you go upward, what is delta Y? This distance. This is delta Y. Okay, so if you want to calculate what is delta Y, you can simply say that this is a right triangle, and the hypotenuse of this right triangle is equal to the displacement of my block, which is 2 meters. So delta Y is equal to delta S times sine 30, because this angle with the horizontal is 30 degrees. Okay, so again, you will obtain the same result, that the work of the weight is minus W. And why it's negative logically? Because your block is moving upward while the weight tries to push the block downward. So always when you move upward, the work of your weight will be negative, and when you move downward, the work of your weight will be positive. So it's minus W delta S sine 30. So now we computed the work of the weight also. We still have to find the work of the spring. So we go back now to the definition. I want to find the work of a spring on the block. Okay, on the block. Then I will use half K delta S1 square, which is the initial stretching or compression of my spring, minus half K delta S2 square. Okay, now what is delta S1 and delta S2? Concerning delta S1, they said that initially it was stretched 0.5 meters. So I can replace delta S1 by 0.5. And what will be delta S2? Who will tell me? What is the value of delta S2?
2.5.
Very good. Initially, my block was already stretched 0.5. And now it's moving upward, so it's stretching more, 2 meters. So the total stretching will be 0.5, which is the initial value, plus 2. So in total, delta S2 is 2.5 meters. And you can expect that the work of the spring will be negative, because it will try to oppose the upward motion of your block. Okay, and now when you compute all work of forces, you can do the summation. And do you expect that the summation will be positive or negative? The summation of work of all forces. Look, you should see who is dominant. Because I told you initially it was at rest. Since the force P was able to move it, yani P is dominant over the weight action and the spring action. Yani the positive work of the weight is higher than the summation of absolute value of work of spring plus work of weight, because it was able to push it upward. If P was not enough, if the work of P was not enough, then your block will not move up. It can remain in its position, or it can go downward. If the weight, for example, is dominant, if P is very small, maybe the weight will be dominant and the block will move downward instead of moving up. Okay? So we can verify this from the calculation. As you can see here, first they computed the work of P, then for the spring they applied the formula and also for the weight. And now by adding the forces, you will have a net positive work. And this is expected because the force P was able to displace the block upward, opposing the spring and the weight, the spring force and the weight. Okay? Any question on this problem?
Yes, دكتور عندي سؤال.
No.
بس الموشن هذه الفورس تبع السبرينج ما عرفت
اوكي لا نيجاتيف لانه انت your spring is stretched. Okay, so how will be the action of your spring on the box لما البوكس يكون عم يطلع and it's stretching the spring, السبرينج حيشد فيه لتحت صح؟
اوكي بس دكتور انا ضيعني هي مش ملزقه البلوك بالسبرينج ولا مبالغ؟
بلا ملزقه بلا.
اوكي ثانك يو.
اوكي هيدي الفيجر لازم يعني منا كتير دقيقة، لازم يحطوا لك هيك. اوكي okay, now we have introduced the work of a force. Now we will introduce together the principle of work and energy. يعني how to relate the variation in energy of the particle to the forces acting on it. Okay, so first to derive the principle of work and energy, we will start from the Newton law. Okay, you know that as we have seen together, in work only forces along motion will do a work, while forces perpendicular to motion will not do a work. Therefore, we can define work and energy starting from normal tangential frame. So if I have a curved motion, then I can decompose my forces into tangential forces, which are along the path of motion, and normal forces, which are perpendicular to the path of motion. And going back to our definition, normal forces will not do a work because they will be always perpendicular to motion. So only the tangential forces will perform a work. This is why we can say that sum of work of external forces is just restricted to sum of work of tangential forces. Okay? Now, by definition, AT can be related to velocity because you know that from first chapter we have taken together, chapter 12 in kinematics, we have seen that we have AT ds equals to v dv. Okay, so AT can be related to velocity and position. And since in work and energy we want to find a relation between the work and the variation in energy of the particle, we can think about this relation now, okay? Because we want to see how, with motion from one position to the other, how the energy will vary. This is why we will use this differential equation, which is independent of time. And then we can replace AT in sum of T equals MAT. We can replace it by its expression. Okay, so you can replace AT by V dV over dF. Let us try to do this. So we can write that summation of integral from S1 to S2 of T ds will be equal to, we will replace the value of, so this represents the external forces acting on a particle. So this is sum of external forces work. Okay. Now we will replace first Ft by MAT. Okay. So in the first step, I can put instead of F TMA, so it will be integral sum of integral from S1 to S2 of MAT ds, MAT ds. And now if you replace AT by its value, or directly here you can replace AT ds, okay, by its value, which is VdV, you can say then that the summation of work, external forces work, can be written as summation of integral from V1 to V2 of MVdV. Okay, so now in this way we have changed variable. Now we integrate with respect to velocity, and we know that m is constant. So for cases of constant mass, I can take the mass outside of the integration, and now I can perform my integration with respect to velocity. So I know that integral VdV is V squared over 2. So I deduce that in case I want to calculate the variation, when I have any variation in position, I can say that sum of work of all external forces between state 1 and state 2 can be calculated as the variation in kinetic energy. It's half mv2 squared minus half mv1 squared. This is the principle of work and energy. The principle of work and energy relates work of forces acting on a particle to the change of the kinetic energy of the particle. Okay? Any question on this? Okay. Now, sometimes you can see the principle of work and energy in another form. So just here, if you take half mv1 squared to the other side, okay, and in Hibbler book, the annotation for kinetic energy is T. So T1 is the kinetic energy at state 1, it's half mv1 squared, and T2 is the kinetic energy at state 2. So you can say that we can write that sum of work between 1 and 2 of all external forces plus the initial kinetic energy T1 is equal to the final kinetic energy of the system. Okay, so this is another way to state the work and energy principle, saying that the particle's initial kinetic energy plus the work done by all the forces acting on the particle as it moves from its initial to final position is equal to the particle's final kinetic energy. So now you can expect that if I have a net positive work, then the kinetic energy will increase, while if I have a net negative work, then the kinetic energy will decrease. Let us do some application on work and energy. Just before, in case you have a system of particles, you can also apply the work and energy for a system of particles, okay? Instead of just taking one particle. The whole idea then will be to do the summation of kinetic energy for all particles at state 1, plus summation of all external forces work between 1 and 2 is equal to summation of kinetic energies of all particles at state 2. Okay, and we will see how to apply in general in which problems we need to take a system. Sometimes Considering a system of particles will simplify the analysis. We will see how. Let us take a small example. If we have a block P moving on a rough surface, okay, then what are the forces acting on it? We are applying a horizontal force on it to move it, and due to roughness, due to the rough surface, you will have a friction developed between the surface and the block, and this friction will try to oppose motion, and it's given by mu kn. So whenever you have sliding, if you remember, whenever we have sliding between two surfaces, the friction will be kinetic and not static. And of course, we have the weight force and the normal force. Now, in case you want to apply here the principle of work and energy, you will apply it in the direction of motion. Direction of motion is the horizontal, okay? Since I want to apply it along the horizontal, then I have that sum of work, okay, between state 1 and 2 is equal to summation of work of all external forces. Now, please pay attention. When we say work and energy, then we should pay attention that all forces perpendicular to motion will not do any work. So here, for example, the direction of motion is horizontal. So no work for the weight, no work for the normal. We will only have the work of P and the work of F, okay? And then we can write that the initial kinetic energy of the system plus, now we will add work of all external forces. So we just have the work of P and the work of F. Since P is a long motion, then it has a positive work, and assuming it's a constant force, then its work will be P times the displacement distance F. While for the friction, since it's trying to oppose motion, so it's a negative work. And here, if you want, you can just say it's minus mu kn times S. Or if you apply the rule of integration, which is integral F the friction cosine theta ds. Here, what is theta between the, in this case, what is theta between F and ds? What is the value of theta?
I.
Very good, it's pi. So you have that the friction is opposing motion. So since theta is equal to pi, then cosine pi is -1. And you can directly do it, no, it's clear, it's directly opposing the force. And you can directly put minus F times delta S, okay, times the displacement S. Now, since F is a friction, kinetic friction, we can find it from calculating the normal. So F is mu k times N. And then we multiply it by S to get the work, equals to the final kinetic energy, which is half mv2 squared, okay? Any questions on this?
دكتور
Yes.
هو هان حسب البي اس ماينس يو كي ان الفاليو تبعها بنشوف اذا الكايناتيك انرجي كبرت او صغرت.
لا، هي الفريكشن على طول حتكون نيجاتيف، اوكي؟ بس شو بيحدد اذا الكايناتيك انرجي حتزيد او حتنقص؟ حسب مين الورك تبعه اقوى، البي او الفريكشن، اوكي؟ يعني انت الفريكشن لحالها الورك تبعها نيجاتيف، والبي الورك تبعها بوزيتيف، اوكي؟ بس شو اذا الكايناتيك انرجي بتقل، يعني الورك done by P بيكون اصغر من الابسوليوت فاليو اوف ذا ورك done by the friction، اوكي؟ بينما اذا الورك اوف P اعلى من الورك اوف فريكشن، ساعتها الكايناتيك انرجي بتزيد، اوكي؟
اوكي ثانك يو.
Any other question? Oh. So let us continue. Let us do an example. The 17.5 kilonewton car is traveling down the 10 degrees inclined road at a speed of 6 meters per second. If the driver jams on the brakes, causing his wheels to lock, determine how far as his tires skid on the road. The coefficient of the kinetic friction between the wheels and the rod is given by mu k equal to 0.5. So in such a problem, okay, how يعني هلا it's clear for you that we will use work and energy, but in exams, how should you think? You have here an initial speed, 6 meters per second, and you know that the final speed will be 0 because they want you to determine the distance before it will stop. Okay, so when you have initial velocity, v initial is known, v final is known, and they are asking for a distance. Okay, the easiest way to solve will be work and energy. Of course, you can use other methods. And for example, you can tell me I can do Newton law, I can find deceleration A, and then I apply the relation independent of time, v square final minus v square initial equal to 2a delta s, and I get s. It's true. But you will do several steps in this case. You should do an equation to get a, then you should do the relation independent of time to get s. So while work and energy will give you just this in one equation. Okay, so always try to use the method that is the easiest one and will not require a lot of time. So now here we need to determine s, so we need to write the principle of work and energy. To be able to do it, we should first do the free body diagram. So we determine what are the external forces acting on our car. We have first the weight, which is always vertical. We have the normal reaction, and here, since you are using your brakes, and there is no driving force, and the engine is not working, so you will only have the deceleration due to friction. So this is the friction always parallel to contact along the contact line. So this is mu k n. This is n, and this is the weight. Okay. So now, first, we need to determine the work of these forces. For n, as usual, work is 0 since perpendicular to motion. Okay. Now, for the weight, here also we have several methods. Okay. Use the ones that you find easier. And I find here, for example, it's easier to project the weight. So if you just consider this line, this is the perpendicular to the incline. The angle here will be 10 degrees equal to this one because the weight perpendicular to horizontal, and this one is perpendicular to the incline. So this is 10 degrees, and therefore the projection of the weight on the direction of motion here it's positive. Okay, لأنه أصلا it's logical when you are going down, then the weight will help you in motion. Okay, so here the work will do a positive work. The weight will do a positive work. UW will be equal to the projection, which is plus W sine 10 times S. Okay, so since we don't know S, we will express the work as a function of S. Okay, now we still have the work of the friction. The friction is opposing motion. So for the work of the friction, it's minus mu kn times S. Okay, so because the angle is pi, and cosine theta is -1. So now, what do you expect? Who will be dominant, work of weight or the weight of work of weight or the work of the friction? مين حيكون أكبر in absolute value? To be able to answer this question, you should know what is happening. Do you have deceleration or acceleration here?
Deceleration.
Deceleration. Your initial speed was 6. Your final speed, V final, is 0. So the friction will have a dominant effect, and you have a positive work for the weight, okay, but the negative work of the friction will be much larger. This is why the kinetic energy will decrease, and you will see this in the equation. Okay, so now if I write my equation, in order to be able to write my equation, I need to find n, because you know that the friction is function of n. In order to find n, what should we do? N is along the perpendicular to motion. Okay, this is n. So to find n, we should do sum of forces along what? Along this line. Along the perpendicular to motion, this is y prime if you want. Since no motion along y prime, you can say that sum of fy prime is equal to 0. And then if I project my forces on y prime, what do I have? I have plus n and minus w cosine 10, because the angle here is 10 degrees. The friction has no component along y prime because it's along x prime. So minus w cosine 10 equals to 0. So this equation will help you to get the normal and the unknown n. And once you get n from sum of y prime equals 0, you can find f, because f is mu k times n. Okay, and now you are ready to apply your work and energy theorem, where the only unknown will be the displacement distance f. So if I replace in the work and energy, I have T1, which is the initial kinetic energy, which is half m v square. V is 6. Here they gave us the weight, so we should divide by g to get the mass. It's 17.5 kilonewton. This is why they multiplied by 1000 to have Newton unit. Over G, we will get the unit in kilogram for the mass. Plus, now for the work of the weight, it's positive. It's plus W sine 10 times S. While for the friction, it's minus the friction times S. And the friction force is mu Kn. So in this equation, as you can see, your only unknown is S, since the final kinetic energy is known to be 0. So you can get the distance S. Okay? Any question on this? Okay, so let us continue. Another problem. The plate P is tied down so that the 0.4 meters long cords keep a 1 meter long spring compressed 0.6 meters when nothing is on the plate. If the 2 kilogram box is placed on the plate and released from rest after the plate is pushed down 0.1 meter, determine the maximum height the block will rise in the air and measure as measured from the ground. I will repeat in brief the given. We have here a plate P, and this plate is forced to be at a maximum distance of 0.4 meters from the ground, okay? Because you have here the rigid links. These rigid links can be compressed, okay, but cannot be stretched more than 0.4. يعني as you can see here, when you compress, they will deform. But when they will be straight, يعني their maximum distance from the ground is 0.4, since يعني they cannot be stretched. Okay? So this is why they will force my plate to be at a maximum distance of 0.4 meters from the ground. And since they are connected to a spring which has a non-stretched length of 1 meters, then they will force my spring to be compressed, because since the unstretched length is 1 and the maximum distance to the floor is 0.4, so of course my spring will always be compressed. Now, at the initial state, it was already compressed here 0.6 meters, because you know delta L is L final, the length of the spring, minus the unstretched length L0. So here in this figure, just before putting anything, what was delta L? Delta L was 0.4 minus 1 equals to minus 0.6. Okay. Now this was the zero state. يعني ما عملنا شيء. We have considered a box. We put the box on the plate. Then we push with our hands the box 0.1 meters down. So this is my initial state. Okay, this is state 1. At state 1, what do I know? At state 1, my block is at rest. V1 is equal to 0. And what is the stretching of what is the compression of my spring at this state? What is delta L at state 1 here? Delta L1 is equal to L final, L spring at state 1 if you want, minus L0. At this state, the length of the spring is 0.3 meters. So I have that delta L1 is equal to 0.3 minus 1, which is equal to minus 0.7 meters. Okay, now this is my initial state. Now I will remove my hand, and when I remove my hand, the block will begin to go upward. So we will have conversion of kinetic energy, of potential energy to kinetic energy. Okay, now let us see what will happen. The question is, what is the maximum height reached by the block? You can do this problem in several ways. You can divide it into steps, and you can do it in one step. For me, I advise you to try to do the minimum number of steps. So here, you can directly apply between the initial state and the maximum height state. Yani, if you want, I will put the different states you have, and we will try to do first from the initial to the final, and then we will do an intermediate case. So in case you want to take an intermediate case, the intermediate one will be when just the block will leave the plate. Okay? Because look what will happen. In a first stage, the plate and the box will move together until the spring reached 0.4 meters. Once once the length of the spring will reach 0.4, the spring cannot anymore follow the block because the plate is restricted to be at a distance of 0.4 meter from the floor by the 4 rigid links here. Okay, so at state 2, what will happen? You will have delta L2 equals to minus 0.6, and your box will have a certain velocity v at state 2. Okay, this will allow it to continue its motion without the spring, and we will have separation between the plate and the box. And finally, in the third stage, we will reach the maximum height. The maximum height is just characterized by V3, so this is state 3. At state 3, V3 is equal to 0. And what is delta L at state 3? What is delta L of the spring at state 3? غيرت شيء delta L؟ No. انتبهوا. الدلتا L كانت 0.06 وبعدها -0.6 صح؟ يعني أنا spring من بعد ال 2 من 2 ل 3 السبرينج غير position شيء؟ My spring didn't change position. Okay, يعني I can consider إنه بعده إذا بدي آخذ كسيستم, if I take as my system البلوك when moving from 1 to 3 مرق بفاز السبرينج عنده effect between 1 and 2 لأنه delta L was changing, but between 2 and 3 delta L ضلت هي ذاتها والسبرينج ما بقى عم يعمل force على البوكس. يعني كمان فينا نكتب إنه delta L3 is equal to minus 0.6. يعني spring بعده محله بين 2 و 3, so spring didn't do any action between 2 and 3. Okay, هلا now instead of dividing into several steps ما في لزوم, I can directly apply work and energy من 1 to 3. Okay, if I apply from 1 to 3, I have that the initial velocity v1 is 0 والfinal velocity كمان is 0. Between 1 and 3 I can directly write that sum of work between 1 and 3 is 0. And between 1 and 3, what are the forces that are doing work? شو هن الفورسز acting on the block between من 1 ل 3؟ If I ask you to draw the free body diagram of your box, okay? هلا هون في two stages مظبوط. في أول stage بس يكون على البليت بيكون في الويت والسبرينج، اوكي؟ ونحن مثل ما شفنا انا وياكم انه من دلتا ال 2 لدلتا ال 3 ما تغير شيء، يعني السبرينج ما عاد عمل افكت، يعني بس السبرينج حيشتغل from 1 to 2. Okay, so now we can write that between 1 and 3 we have the work of the weight plus the work of the spring equals to 0. Okay, now since we are applying from state 1 to state 3, for the weight, the work of the weight, of course, will be negative. Why? Because the block is moving upward. Okay? So just I will have to apply the formula. Here minus W delta Y. Now concerning the work of my spring, مثل ما قلنا السبرينج بس حيشتغل between 1 and 2 لأنه from 2 to 3 ما تغير شيء. يعني أصلا شو ما كتبت حتصل هي زد، يعني إذا بكتب دلتا L3 أو دلتا L2 it's the same. So I can write minus W delta Y plus for the spring, the work of a spring on the box هو by definition half K delta L1 square. هلا for the second stage أو بتحطوا delta L2 أو delta L3 ما أصلا هي ذاتها، يعني half K delta L1 square minus half K delta L3 square. Equals to 0. Now, what is delta Y? Delta Y is simply from between، يعني delta Y from 1 to 3 نحن عم نشتغل between 1 and 3 مظبوط. From 1 to 3 delta Y is Y final at 3 which is if I take the reference as the ground Y3 هي plus H Y1 هي the initial height هي 0.3. So delta Y will be replaced by H minus 0.3. So the equation will be H minus 0.3 هيدا delta Y times minus W and times minus mg. Now for the work of the spring I have plus half K. What is delta L1 square مثل ما شفنا أنا وياكم؟ delta L1 is 0.7 لأنه هي 0.3 minus 1. Okay, بما انه عم بعمل سكوير يعني مش مهم النيجاتيف ساين, so it's half k times 0.7 square because the initial compression is 0.7 while the final compression is 0.6, so minus half k times 0.6 square. So as you can see in this equation, k is given, it's 200 Newton per meter. As the mass is given, so the only unknown is h. So this equation will directly allow me to calculate the value of the maximum height from the ground. Now, إذا بدكم تعملوا intermediate steps, you can, بس ساعتها بدل instead of applying one time work and energy, you will apply it 2 times. The first time will give you what? Will give you the velocity of the block just before leaving the plate. Okay, يعني first, the second method is to divide the motion into steps. Phase 1 هي لما كان عندي contact between the spring and the box. So in order to determine what is V2 when the box will leave the spring, we can write that sum of work between state 1 and state 2 is kinetic energy at state 2, which is half mv2 square, minus the initial kinetic energy is 0 because the system starts from rest. Now, concerning from state 1 to 2, what are the work of forces? We have the work of the weight. فإذا هيدا state 1 just here, and this is state 2. What will happen between state 1 and state 2 is that delta y is just 0.1 meter. فهنا هي 0.4 minus 0.6. So you will have for the weight, the work will be minus mg times 0.1. Now for the spring force, okay, it is equal, the work will be plus, at state 1, delta L1 is 0.7, يعني plus half K times 0.7 square. At state 2, delta L2 is 0.6, so minus half K times 0.6 square equals to half mv2 square. As you can see here in this equation, the only unknown is v2. Okay, so from this relation you can calculate what is the velocity of the box when leaving the plate. And now you can just apply work and energy between 2 and 3. ساعتها between 2 and 3 ما في work of spring لأنه خلص the spring is not anymore in contact with the block. You only have the work of the weight from 2 to 3. وساعتها from 2 to 3 you can write that the following. So let us apply it from 2 to 3. Between 2 and 3, what can you write? You can write that from work and energy, and the initial kinetic energy is half m v2 square. Now, concerning the work, we only have the work of the weight between 2 and 3. So the weight is doing a negative work, and the negative work of the weight is given by minus W delta Y equals to the final kinetic energy, which is 0 because the box will stop. Now, what is delta Y in this equation? I have Y3 minus Y2. Okay, Y3 is equal to H, Y2 is equal to 0.4. So if you replace here delta Y, it's H minus 0.4. Anyway, here if you replace half mv2 square by the expression you get from the first relation, ترجع بيطلع لكم الwork and energy اللي عملناه بأول step. So here H minus 0.4. فإذا بتنتبهوا هونيك طلع معنا شي 0.1، هون عنا H minus 0.4، بيرجع بيطلع لنا إنه work is related to H minus 0.3. Okay, يعني هي ذات الريليشن اللي جبناها سوا قبل. Okay, so the value of H will be the same if you do the first method or you do the second one. Okay, any question on this? Please ask if something is not clear for you, okay? Do you find that you are going fast or it's fine?
It's fine though.
ايه
Okay.
It's
محمود
fine. ده هينين.
Okay, good. Yeah. Another problem.
دكتور
Blocks. No. Yes.
كان بدي أسألك عن البارسيال هلا بعد شوي سوري.
Okay. Blocks A and B have a mass of 10 kilogram and 100 kilogram respectively. Determine the distance B travels from the point where it is released from rest to the point where its speed becomes 2 meters per second. هتشوفوا هون انه في كتير problems حليناهم سوا قبل، هنرجع نحلهم بالwork and energy because this is to tell you that work and energy will facilitate a lot the solution. إذا بتذكروا بالchapter 13 أخذنا problem قريب، كان عندنا blocks system of pulleys وحليناه نيوتن لو وشفنا قد ايه طويل، يعني بلشنا انه لقينا الريليشن اكيد بالموشن اوف A and B. رجعنا اخذنا سيستم A لحال، سيستم B لحال، عملنا نيوتن لو، طلعنا سيستم اوف equations، تحللنا جبنا الاكسلريشن، ورجعنا قلنا انه since A is constant we can use B square final minus B square initial equals to 2A times delta S, which is a very long method. هون حنشوف how by using work and energy we can reduce a lot the time of solution. Okay, so here the question is to find the distance traveled when the speed becomes 2 meters per second. Okay, يعني شو بنعرف بهالبروبلم؟ قالوا لنا انه it's starting from rest، يعني بنعرف انه V initial of the blocks 0، وبنعرف الفاينل speed of B، بس انتوا اكيد بتعرفوا انه بس يكون في pulleys we can find VA2. Okay, يعني نحن we know VB2, so we know initial and final states and we want to find a distance. عطول بس يكون في هول ال variables distance initial و final velocity فكروا بالwork and energy. Okay, now what system to take؟ هون it's very important to select well the system، لأنه إذا بيجي باخد A لحال و B لحال ما بكون عملت شيء. يعني بصير بدي أكتب work energy ل A work and energy ل B، فرجع ال number of equations كأنه عم بعمل نيوتن لو، ما استفدنا بشيء. I should take a system بطريقة in one equation to solve. Okay, and the importance here of taking the whole system رح أقول لكم شو هي. انتوا إذا بتاخدوا A لحال the tension in the spring will do a work. إذا بتاخدوا B لحال the tension will do a work because B is moving, A is moving. But if you take like this the system مع ال pulleys هون, you have the external forces شو حيكونوا؟ The reaction at the ceiling level, the tension at the ceiling level, and the weight of B, the weight of A. بس ليش ما بيهمني هول الرياكشنز والتنشن؟ فيني ما اجيبهم. why I don't care for them؟ شو الورك تبعهم هول الفورسز؟ الرياكشنز والتنشن at the ceiling level.
زيرو لانه مش على البي.
very good. زيرو لانه applied على fixed point، يعني انت اذا عندك force applied على شيء fixed يعني ما عم يتحرك فيها تعمل work شيء. ما الwork by definition هو له علاقه بالديسبيسمنت. هول الفورسز are acting at fixed points، يعني الwork of reaction force هون والwork of tension force على السيلينج كلهم زيرو. فساعتها بالwork and energy مش حيبينوا هول الفورسز، خلص ما بعوزهم. Okay, so no need to get any tension. I have only the work of the weight of A as external force and the weight of B. Okay, so taking the whole system will simplify a lot my analysis. So what I can write now, since I have the pulleys are massless, فما عندي غير A will be. So I can write that kinetic energy of A at state 1 plus kinetic energy of B at state 1, hey, the sum of kinetic energies of particles, plus sum of work of forces between state 1 and state 2. وشو هن قلنا الفورسز اللي عم يعملوا work؟ WA and WB. Okay, equals to the summation of kinetic energy at state 2 اللي هي TA2 plus TB2. هلا نحن حنجرب نكتب equation وحده نجيب فيها ال unknown اللي هي distance. So we will try to get one equation with one unknown. But to be able to do this, we should relate motion of A and B إجباري. لأنه you know that هلا initially the system is at rest، يعني أكيد TA1 و TB1 0. But to be able to find TA2 and TB2 بنعرفها لأنه بنعرف ال final velocity of B 2 meter per second. بس نلاقي TA2 بدنا نلاقي V2، يعني بدنا نلاقي VA2 half لأنه TA2 هي half MA VA2 square and VA2 is not given. Okay, but always when you have a system of pulleys, remember that you can relate the velocities of blocks and you can relate their acceleration and you can relate their displacement. هون شو بهمكم تعملوا relation مش للاكسلريشن، هون بهمكم تعملوا relation between velocities and relation between displacement. Okay, because in work and energy I need the displacement and I need the velocity. Okay, so let us do this. This is my system. I have just one cord and I have two bodies in motion, so I need one coordinate for B, S of B. I always select a reference line that is fixed. فيني اخذ مثلا ceiling او فيني اخذ كمان line passing by the center of the fixed pulleys. يعني the centers that are fixed إذا بتكون هي البولي حتبرم أكيد around the fixed point. So here this is a good choice. هيدي constant ما بتأثر على شيء هيدي البort. It's a constant يعني you know that when we put the total lengths we lump all constants together. Okay. So we can say now that we have just two coordinates, one for A, one for B, and we will write the total length of the chord function of SA and SP. So to do it, we have, let us follow the chord. This is a constant. You have SB, constant, SB another time, and salana to SB, constant, SB a third time, another constant, SB a fourth time, and for SB, this is a constant, and this is SA. So we can write for the chord that SA plus 4SB equals to constant. And now we are ready to derive. هيدي relation بتعطيكم VA plus 4VB equals to 0. كمان بتعطيكم relation between displacement. If you remember عملنا problem together إذا بتتذكروا بالchapter أول chapter قلنا إنه هيدي relation is between instantaneous velocities. فإذا relation apply for instantaneous velocities أكيد it apply for average velocities. يعني كمان فيني أكتب إنه VA average plus 4VB average equals 0. رح نعرف إنه average velocities are calculated as delta S over delta T. يعني I can replace V average by delta SA over delta T. And I can replace VB by delta SB over delta T. So I get the delta SA over delta T plus 4 delta SB over delta T equals to 0. And now delta T can be simplified. So I can get a relation between displacement of A and displacement of B. So delta T بتروح. Now knowing إنه VB final is 2 meters per second, I can write that VA at state 2 is minus 4 VB at state 2. It's equal to minus 8 meters per second. And for displacement, I can, since I am interested in the distance traveled by B, يعني بدي delta SB, so I will express delta SA function of delta SB. Delta SA can be replaced by, from this relation, by minus 4 delta S of B. And now, the only unknown in my work and energy theorem will be delta SB. Okay, so just I have to do a replacement. Let us see what are the sum of works. Okay, قلنا إنه بالwork and energy عندنا sum of work between 1 and 2. وقلنا إنه بس the work of A and the work of B, weight of A and weight of B are doing work. Now, how to express the work of a weight? نحن شفنا إنه إذا coordinate upward يكون الwork minus W delta Y. بس هون how is S? How is coordinate S? Downward. And what is the expression of the work? Minus W delta S. Okay? This is why I can write here that work, sum of work here, minus WA, which is the weight of A, times, sorry, plus, لأنه قلنا S downward, okay? Plus WA delta SA. This is the work of weight of on A, plus for the work of weight of B plus WB delta SB. And I can replace delta SA by minus 4 delta SB, so that the only unknown in my work and energy will be delta SB. Okay, let us see how to replace it in the work and energy theorem. So here you can see the whole equation. This is the summation of kinetic energies at state 1, half MA VA1 square plus half MB VB1 square. But since the system is starting from rest, so I can say that these values are 0. Now concerning sum of work between 1 and 2, I have, as you can see here, these 3 forces has no work because they are applied at fixed points. So I will only have the work of weight of A, which is plus WA delta SA, since SA is positive downward. And for work of weight of B, it's plus W delta SB equals to the final kinetic energy of the system, اللي هي half MA VA2 square plus half MB VB2 square. Okay, and now if I replace the delta SA by minus 4 delta SB, and I replace VA by 2 minus 8 and VB by 2, because you know that VA is minus 4 VB. So the only unknown, so I can say instead of VA it's minus 8. The only unknown in this equation will be delta SB, so I can calculate. Okay, so just I have to find the relation by using the Pulley system. So I get delta SA is minus 4 delta SB and VA is minus 4 VB. Then replacing in the principle of work and energy, I can get delta SB. And since delta SB is positive, this will tell me that B is moving downward while A will move upward. So the work of weight للB هيكون positive, while the work of the weight of A هيكون negative. Okay? Any question on this? This is mainly the work and energy chapter. It's a very simple chapter. Hey, the first relation we applied. Next time we will see together the definition of power efficiency. And oh, if you can we take 10 minutes more from your time?
Yes, sure, doctor.
أي ساعة your
لحظة
second?
دكتور، ما فينا
أي ساعة your
بعد
second
10
class?
دقايق.
About 10 minutes?
Yes.
طيب اوكي خلاص we continue this on Wednesday. Okay. يلا باي.
Okay, doctor. Thank you.
Welcome.
Have a nice day.
Bye, doctor. Thank you.
Bye.
Merci, doctor.